So, welcome to lecture 4. Hopefully you've had fun so far in the class. You covered 3 lectures, and yesterday was an introduction to labs, which you're going to have fun with over the entire semester. It'll be fun. So just to warn you, labs will cover just part of the lecture, as I will also talk about. We have a lot of interesting things to cover in this class. You'll get exposed to processing paradigms. Unfortunately, labs can only go so far because there are only so many weeks in the semester. So you'll be able to design a very simple modern processor on an FPGA, program the FPGA hardware, and have fun with it. But you won't be able to explore the more advanced paradigms that we're going to talk about in this lecture. So, but hopefully it'll be fun. It'll give you a very good glimpse of how things are designed today. So let me give you the agenda today, even though the title is, the lecture title is Combination. By the way, can everybody see the slides well? There's no glare. Everybody's good? Good, okay, I see all thumbs up. You can, if there's something wrong with the slides or something that you cannot see, please shout. I think that's a good mode of communication over here, so that we can fix the problem before you stop listening to the lecture. Right? It's good to indicate your problem quickly so that we can change. Okay, so this is the agenda that I have today. Basically, I'll give you some assignments for this week and the next. We're going to wrap up the computer architecture mysteries lectures. I'm going to give you some more takeaways. Hopefully you had fun with Frank in the first week. We're going to discuss very briefly a little bit more about course logistics. I'll introduce myself since I wasn't here last week. And then we're going to jump into combinational logic circuits and design. As I said yesterday, we're going to start with the transistor. And we're going to start with the transistor as an abstraction, like a wall switch, to build everything on top of that. So today is a very critical lecture, actually. Everything builds on the understanding that you developed today. So hopefully you'll pay attention, not just to this lecture, but all of the lectures. But the good thing is you have the videos online, so if you miss something, you can go back and watch the videos. And you can play them at the rate that you wish to play them at. Some people tell me they like speeding it up by 2x. Some people tell me they like slowing it down by 2x. So you can do whatever you want. That's the beauty of having offline videos. You can adapt the learning rate to the rate at which you like receiving things, right? Unfortunately, in a classroom setting, it's very difficult to do. That's why having this offline video helps you adapt to that heterogeneity in the learning differences between people. Okay, so let me give you assignments first. This is one assignment. Basically, remember you have the homeworks also that are optional that you should definitely do. Even though they're optional, you should definitely do them because they will help you prepare, understand the material, prepare for the exam also. I know that's not your main criterion, but that's something useful to do. So basically, why study computer architecture? Why is it important? We motivated that in the first 2 lectures, but I would like you to watch my inaugural lecture at ETH, which I delivered in May 15th, 2017. I think it's May 15th. Oh. Like any memory, my memory is also not good, right? You need to refresh it somehow. And how do you refresh it? You go back and figure out what day is it. It's refreshed at that point. And then the charge decays over time, and then you need to refresh it again. Okay, basically, watch this lecture. This lecture is a concise coverage of the state of computer architecture today. You will see some slides that are similar to what you've seen, but you will also see why it's so important today. And this lecture was open to public, so it's actually accessible to public. Hopefully you'll like it. And I'll give you an optional assignment, and I'll give you a 1% extra credit if that incentivizes you to watch it, but you'll have to do this optional assignment. So watching is required. Assignment is optional, meaning what is the assignment? Write a 1-page summary of what you've learned, essentially. This should be really easy to do, frankly, and email us. So what are your key takeaways from the lecture that you watched? What did you learn? What did you like or dislike? What was surprising to you? What was boring to you? You can basically tell about anything in that 1 page. I like hearing about what's surprising in general when people watch new things and learn new things. So I will suggest doing this assignment, and this is my carrot for you, so you get 1% extra credit. So this is extra credit. Yes?
What do you mean by ETH?
Say it again? No, this is, so the course consists of, let's say, 100 points. You get 1% additional point to bump you up, basically, if you do this. Make sense? Okay. Okay, so that's one. I think you'll have fun with it. And also, it'll help you reinforce some of the things that we cover in this lecture and also learn about some things that may come up that is happening in computer architecture today. So the other assignments, unfortunately, you don't get credit for these, but you should definitely do these because they will be important for your understanding of this lecture, next lecture, and actually the 4 lectures ahead. And that is basically reading these books. Actually, I don't have the books with me, but this week we're going to cover combinational logic, and that's covered in Pat and Patel book, chapter 3 until 3.3, and Harris and Harris book, chapter 2. So we have these 2 different books because the material we cover is actually not covered in any single book. Some of it is covered in Pat and Patel, some of it is covered in Harris and Harris. Some of it is not covered in any textbook, as far as I know, until I write that textbook, which will hopefully happen someday. But don't count on it this semester. So that's why you should do the readings in both books. And both books have different styles, advances and disadvantages. I would suggest doing the readings. And this is for this week, so do it as soon as possible. If you haven't done it today, that's fine. After the lecture, you can do it, and you can understand the concept in a little bit more detail. Next week, we're going to continue combinational logic a little bit and then cover hardware description languages and Verilog. So that's covered in Harris and Harris chapter 4 until 4.3 and 4.5. That's not covered in Pat and Patel, so that's something that doesn't exist in the Pat and Patel book. You'll have to use Harris and Harris for that. And then we're going to go into sequential logic, and these are the required readings for that. So by the end of next week, roughly, this is not going to end next week. I think we're going to spill over to the other week after that. But please try to stay on track. Make sure you're done with Pat and Patel chapters 1 through 3, inclusive, and Harris and Harris chapter 1 through 4, inclusive. And so one of you asked the question, is there, if there's an asterisk chapter, should you read it? I would recommend that you read it because it gives you material that will help you understand the details. And once you understand it, you can actually solve any kind of problem that's thrown at you much better, I think. So please do the readings. I know there's a lot of readings, but that's how you get started, and that's how you learn the details. If you really want to understand how things are working, I think there's no other way than going into more detail. And I can only convey so much in a lecture. Okay, does it sound good? Good. Okay, so this is the recap of what you covered in the first 2 lectures. Remember, we covered the 4 mysteries. Hopefully you remember what these are: meltdown and specter, row hammer, memory performance attacks, refresh that I just talked about, and radar. I think these are very interesting things, 3 of which I was very heavily involved in, as you know. And meltdown and specter came about because people were very involved in hardware security. So let me cover the takeaways very quickly so that we can jump into why we're doing what we're doing in this course. Basically, we said that breaking the abstraction layers between components and between different levels of the transformation hierarchy and knowing what's underneath enables you to understand and solve problems. And this course is all about that, actually. And the second takeaway was, if you remember some of the solutions, you want to have cooperation between multiple components and layers that can enable more effective solutions and systems. And we've seen this in solutions to the row hammer problem, potential solutions to the meltdown and specter, which we didn't talk about, solutions to memory refresh problem, memory performance attacks. Even though we didn't cover solutions in detail, you can guess that there needs to be a cooperation across the multiple layers. So we're going to break down those layers and see some of them in this course. Clearly, we're going to focus on this part, but today we're going to start with logic, as I said. So logic is definitely part of the focus of this course. And if you stretch it, the expanded view will cover this one. And the required video assignment, lecture video, the inaugural lecture video is arguing for this approach. So you will see that. So okay, some takeaways. Basically, I strongly believe that it's an exciting time right now to be understanding and designing computing platforms. And that's much better there now. Because there are many challenging, exciting problems that we have today in design. And not only in design, but at the higher levels also. Like, how do we enable very efficient machine learning algorithms? I don't think we know that yet. We throw a lot of machinery at machine learning today. But how do we do that very efficiently in a cell phone? Nobody knows at this point because nobody can really train those models in a cell phone today. And these are problems that no one has tackled or thought about before, and you've seen some of them also. These are all, the 4 mysteries that I mentioned are all discoveries at the time, actually. They were things that were discovered. Now they're known, of course. After you know something, hindsight is 20/20. But before you know it, it's not discovered yet, right? So we have yet to discover many, many other things. And these discoveries can have huge impact on the world's future, right? And you guys will be building the future going forward. So that's why it's really important for you to take the fundamentals correctly. I worry a lot about some of the things in the future. For example, how do we do sustainable computing? I think our design principles completely go against that today, and hopefully you'll see the fundamentals and you'll be able to question them in the future. How do we do like more secure, safe, reliable computing? I think that's very difficult today with how we're doing it right now. For example, we're relying on machine learning. People are trying to rely on machine learning in all aspects of life, but it's not clear that we're doing it right because these models are trained based on some data, and data in general tends to be biased. And how do you actually make inference on things that you haven't seen before if your data is biased, right? You may actually have huge problems in terms of safety, privacy, and security if you don't do things well. So, and these are all platform design problems because people build platforms for these problems. And this course is all about platforms. And clearly, we need new mechanisms because we're driven by a huge hunger for data today. We can generate more data than we can analyze today. This is seen in bioinformatics, for example. In genomics, the cost of sequencing a DNA has gone down so significantly that we can now sequence so many DNAs, but we don't have the ability to analyze them well. And we definitely don't have the ability to analyze them efficiently. And that's just one example domain where we can generate lots of data. There are a lot of example domains like video analytics. They're everywhere full of videos. You can argue that that's a good thing or a bad thing, but it's happening. And what do you do with that data? There's lots of issues in terms of security, privacy, analysis, efficient analysis. And like any technology, this could be used for good or bad, but assuming that if you use it for good, like what do you do with it? What kind of applications do you develop for it? Aggregated realism is one example of that. So basically, we can easily collect more data than we can analyze and understand. And that's why we're actually pushing the platforms that we design further and further, squeezing a lot out of them, and they're not delivering yet. That's why computer architecture is very interesting, because it's all about designing these platforms that can do things efficiently, at higher performance, reliably, securely, safely. Of course, these are all design constraints, right? And also we have problems at the lower level, at the technology level, as we've seen in the previous lectures. We're having problems. Technology is not scaling, is not helping us really well. The transistors and the capacitors that we relied on building these circuits are becoming less and less reliable. They're becoming more and more leaky, less and less energy efficient. So how do we actually design systems that are efficient despite we have technologies that are not so reliable at the bottom? Again, technology may not be reliable, but you can build abstractions on top of it that may make it reliable, right? For example, if a computation is not reliable, you do it 10 times, and you figure out the most common outcome. That's called voting. That's called multiple redundant execution. If you do it 10 times, it's 10 redundant execution. You execute the same thing 10 times, and you pick the most common result and hope that that's the correct result. Of course, that may not be correct also, right, if you have too many errors in your computation. So those are fundamental principles of reliability, which we will not necessarily get into, but technology scaling is causing these reliability issues. So in this course, we're going to assume that, like in this lecture, we're going to assume that the transistor we build is going to be reliable. But think about what happens if that changes into the future. Okay, so I actually mentioned a lot of these. Energy is a big problem, reliability is a big problem, security is a big problem. I didn't talk a lot about complexity, but complexity is also a big problem. Because as we try to tackle more and more problems, the systems are becoming more complex. I'm going to show you a pictorial example of systems becoming more complex. So how do you deal with that complexity in the system? Because if the system is too complex, it's hard to reason about. It may also become less reliable. There may be some components that are less reliable than others. And energy becomes a constraint also. So designing complex systems is becoming an issue. And this is actually an area where things are interesting because in this course, we're going to see the perspective of a human designer. You're the human designing a computer, right, and making it work. But maybe in the future, we're going to get help from algorithms that are more automated, like machine learning algorithms, and we're going to use more of them in the system to actually do tasks for us. For example, you covered the memory performance attacks, right? If you had a machine learning-based memory scheduler that did this scheduling intelligently, based on, for example, reinforcement learning principles, maybe it can actually come up with a better solution than a human can, considering all potential possibilities, because humans are not good at considering all potential possibilities given, there's flickering going on over there, given basically different workloads. So think about these while we go through this course. We're not going to go into all of these, of course. We're going to assume things are reliable, assume things are relatively simple, and we're going to build upon that simplicity. But the real world is going to be much, much more different, as you will see when you get out. Okay, so let's talk about some of the things, some of the drivers. Basically, applications are increasingly demanding today, and people are good at dreaming, and applications will always come. So there will be no end to good applications, good workloads. Remember, machine learning was not an interesting application 10 years ago. Today, it's extremely interesting. People dreamt of it, and people actually built platforms for making it fast, not necessarily efficient, fast. And as a result, machine learning is an application that's used pretty much everywhere today, and it's going to be that way going forward also. So there used to be, people used to say, okay, why do we need higher performance systems? We can run every application that we want, right? Of course, as this generation, you should not buy that argument, because as you keep increasing the performance of systems, people will find ways of using that performance. There will be many, many more applications going forward that we haven't enabled yet. Like, can we do, for example, genome analysis in real time in a platform that looks like this, something small, even smaller? I don't know, pick something else like this. If you can do genome analysis at real time very quickly like this, a doctor can take this device, get your genome, and analyze it, and then quickly decide what they should administer you, what they should give you in a life-critical situation, potentially, right? If you don't have this device, you'll have to wait for 2 weeks for your genome to be analyzed. It costs a lot, and it also takes time, and 2 weeks may be really critical under that condition. Okay, so basically there are applications, and as people dream, they will come. And this is one example application. Right. How many of you drive like this? Not many, probably, at least not yet. I wouldn't suggest trying, unless somebody else is driving here, of course, but in this case, you don't have that somebody else. Okay, this is the fun part of it. So these things were not dreamt of. People dreamed of these things for a long time, but they didn't exist before, but now they exist, right? And this is actually a very cumbersome example of it, right? It's a drone that looks cumbersome, but how do you actually design these things that are much more efficient? Okay, so that's application side. On the system side, systems we're designing, we're having really interesting trade-offs today. You were exposed to 4 different mysteries. They're actually examples of these interesting trade-offs. For example, security performance trade-off. We put these complex hierarchies in the system, and they cause side channels, security vulnerabilities. We push the technology to have extremely high capacity in memory, and now it becomes unreliable. Reliability, storage trade-off. We want high capacity because high capacity has enabled this, right? If there was not high capacity memory, this wouldn't be in your pockets right now, because you would make no use of it. And you wouldn't be wasting a lot of that high capacity storing pictures and videos, right? This thing always runs out of storage right now. So you've been exposed to those trade-offs, and we're going to see more trade-offs over here. So this is one trade-off that I like putting up. This is a slide I borrowed from Bill Daly, who was the chief scientist at NVIDIA and a professor at Stanford. And basically, these are some old technology numbers, but I'm going to give you an example. This basically denotes the cost of doing things on a chip and off a chip. What is the energy cost? How much energy does it cost to do a complex addition? You don't need to worry about DP. DP means double precision floating point operation. You'll learn about that later. It's a complex addition, basically. So if you do it on 64 bits, it consumes 20 picojoules. Picojoule is a very small number, basically. A memory access a DRAM read or write, the DRAM that you saw earlier, consumes about 16 nanojoules. So basically, there's a huge divergence between how energy efficient your computation is and how energy inefficient your memory access is. So going to the memory and getting a piece of data costs almost 3 orders of magnitude more than the energy that you use to do a complex arithmetic operation. So think about that. That doesn't sound very good, right? And this is just memory access. If you actually do a disk access to your SSD, it's much higher energy. If you do a wireless network access, it's much higher energy. If you go to a data center somewhere, it's much higher energy. So we're actually consuming a lot of energy today to get the data from where it is into the computing device. And the computing device has become extremely efficient. So we have a huge data movement problem today. What else do I want to say over here? So basically, if you want to add 2 numbers, number 1, number 2, store the results in number 3, and they all are in memory, you do 3 memory accesses to do 1 addition. So you basically consume 3 times 16 nanojoules to do just a simple 20 picojoule operation. By the way, picojoule is 10 to the minus 12 joules, right? Nanojoule is 10 to the minus 6 joules. No, nanojoule is 10 to the minus 9, sorry. 10 to the minus 6 is microjoule. So that's 3 orders of magnitude. 10 to the minus 12, 10 to the minus 9, that's 3 orders of magnitude over there. So think about that. This trade-off didn't exist. So if you go back 70 years ago, if you do this math, if you do your homework, and if you study the systems that were designed 70 years ago, 70 years is 1949, right? Okay, 73, 75 years ago even. It turned out that this was actually much more expensive than a memory access. The cost of a complex addition was about 2 orders of magnitude more than a memory access. So what has changed in the course of 75 years? Any guesses? Like, why has this become much more energy efficient, whereas this didn't become as energy efficient? Has anybody heard of Moore's law? That's essentially the consequence of our ability to scale the transistors. Actually, there are 2 things at play. One is Moore's law. We can actually put more transistors, and we can actually scale the transistors such that they become more efficient. So over the course of 75 years, we were able to scale the transistors such that they became much more efficient, and transistors are the things that do the computation over there. So Moore's law enables us to cram more transistors. There's also the law of technology scaling. It's called Dennard scaling. Bob Dennard is the inventor of DRAM in 1965. He was at IBM. He invented DRAM. He also developed a theory of transistor scaling, which said essentially, as you reduce the size of the transistor, over time it becomes more efficient. And as a result, people have been following that theory, and transistors are becoming more efficient for the course of the last 70 years. Whereas memory access, which is not fully transistor-based, as we will see later on in DRAM, as you have seen a little bit actually, it's really based on the interconnect, the wires. That has not scaled as much. As a result, you have this huge disparity right now. Memory access is much more costly than even a complex arithmetic operation. So think about, I'll put this into perspective. We're not going to tackle this problem in this course. We're going to give you how we're designing the computers today. But future may be different from the today. So you should take away the fundamentals very well, but 20 years from now, the computers may be slightly different because of this trade-off. Okay, so I'll give you one consequence based on our research. This is a paper that we recently wrote with my students and collaborators from Google. Essentially, we examined the really interesting workloads that you execute in an Android phone. How many of you use the Chrome browser? Okay, that's a lot. How many of you use the iOS Safari? Okay, that's almost half and half, I guess. I use the Chrome browser over here. But that's one example workload. The other example workload is TensorFlow machine learning inference engine. If you look at your cell phones, they're doing a lot of machine learning inference to help you. The Siri, that usually doesn't work, for me at least, there's a lot of machine learning, for example. And then you do video processing, video encoding and decoding. So if you look at all of those workloads that you use all the time, if you're playing video on your computers, you're doing video processing. And if you're using an Android phone, that's the VP9 encoder and decoder. If you look at all of those workloads, what's happening is basically more than 60% of the energy that's spent on your phone is spent on data movement. You know, we are calling these machines computing machines, but most of the time they're wasting energy on moving data from one place to another. So think about that. Again, this is food for thought for you. That's why this is really important to understand how these things are built, because this fraction is actually increasing. It may become 90%, and then the question arises, does it make sense to design the systems the way we're designing going forward if this becomes 90%, because we're wasting most of the energy on moving the data from one place to another. Okay, but first we need to understand how we design the systems today. Okay, so that's exactly why I wasn't able to make the lecture last week, so this is the talk I gave at the International Solid-State Conference. It's about enabling in-memory computation. And this, I covered this a little bit in my future computing architectures lecture that you're required to watch right now. But this was given last week. And hopefully you might be interested in that. We're not going to cover this. Unfortunately, this is a paradigm that's going to be beyond this course. But going forward, you may want to know about it, because it's going to change a lot of things. And this was another talk. Okay, so systems are becoming also increasingly complex. I look at this as a past system. So do you think this is the kind of system that you have in your computer? In your cell phone? You have processors, you have main memory, you have storage. Who says yes? Okay, who says no? Okay, more people say yes than no. I will argue for no, because the systems are actually more complex today, because you don't just have a processor chip. Actually, this thing has a lot of accelerators in it. It is a video accelerator. It has a GPU. So it's not just a single chip over here. It's more like this. Well, maybe I added some more over here. So you basically have GPUs. You have heterogeneous processors and accelerators, different types of accelerators, and increasingly FPGAs, also field programmable gate arrays that you're actually going to program in this course. And the systems are becoming more complex, as you can see over here. And memory is becoming more complex. Memory is becoming more hybrid. There's not just DRAM, but there's going to be persistent memory soon, basically memory that doesn't lose its data when it's powered off. Your disk is like that, but disk is slow. Imagine a DRAM-like memory that's fast, but that doesn't lose its data when you turn it off. It's called persistent memory, non-volatile memory. And there are prototypes of it that are coming out, hopefully this year, that's being employed. So modern systems are increasingly complex, and they're going to become more and more complex. That's why this is exciting. Hopefully you're going to be exposed to some of these paradigms that we will see in the course. Well, you're going to be definitely exposed to FPGAs. You may get sick of them, because sometimes they're very cumbersome to program. Okay, so let me recap some of the goals of the course very quickly. Basically, my goal in this course is to teach, enable, empower you to understand how a processor works, its principles and its precedents, as we covered in the first lecture. And I really want to focus on the fundamentals of operation. That's really important. And that fundamentals are going to remain, and if you understand the fundamentals, that's how you can actually change things. And at some level, those fundamentals will help you understand other things in the world as well. But I'm not going to make that judgment call right now. And you will also implement a simple microprocessor from scratch on an FPGA. That'll be the lab components. That'll be the fun part. As I said, simple microprocessor. It's going to be very simple. It's not going to be satisfying to some of you, but that's what we can do in one course. Okay, and you will hopefully, the goal is to hopefully understand how decisions made in hardware affect the software and the programmer, as well as the hardware designer. So hopefully you'll understand the different decisions that we're going to make. And maybe this is one of the most important things, actually. Think critically. That's really important, because if you don't take anything else out of the course, hopefully the course will enable you to think critically. And that will be something that can remain with you for a long time. As I said yesterday, your grade will not remain with you. Nobody will care about it 30 years from now. Maybe nobody will care about how exactly you can explain how a transistor works 30 years from now, but people may care about whether you think critically and whether you really bring value into a problem that you're trying to solve, right? And of course, think broadly. That also helps a lot. And my goal in this course is to give you the broad perspective. We don't want to focus on just one layer. We're going to actually go through layers and layers, and we're going to build up. Okay, and hopefully this will enable you to understand how to analyze and make trade-offs in the design. So these three go together. Okay, slightly more info on course info and more on course info and logistics. Any questions, by the way? Things are good? Okay, so let me give you a little bit more info. I didn't properly introduce myself, although Frank, I think, did a good job introducing me, so I won't cover too much. So basically, I joined ETH in May 2016. Did I do something? Okay, I guess this is better. Somebody decided it's better, it's good. I was at Carnegie Mellon before. I still have a small group there. They're graduating. I got my PhD from UT Austin in 2006. Beautiful town, growing. I worked at many places. After my PhD, I went to Microsoft Research, started the computer architecture group. And the memory performance attacks work was the first work we did actually at Microsoft Research to figure out how multi-core processors that were actually becoming common at the time are vulnerable to that sort of attacks that you've seen. One process can actually destroy the performance of some other process if you run them together in, for example, a cloud-like environment, which means that your cloud provider cannot provide service level agreement guarantees to you if you actually put two programs together on the system. And then I did a lot of work at Intel and AMD during my graduate studies. And more recently, I worked at Google and VMware. And the Google paper that I showed you was part of the work that I've done at Google and VMware. And we looked at a lot of memory system and system level issues over there. You can reach me with my email. This is one email. So you can also email my ETH address or CME address. All of them I receive. That's my website. If you want to meet me, please email me by appointment. If you don't get a response email again, redundancy helps. So it's amazing that the reliability principles are very common across all domains. This is called redundant execution. And we do redundant execution in computers today. Okay, so I do research and teaching in computer architecture, computer systems, bioinformatics, and hardware security. And some of the things that you've already been exposed to, like the row hammer problem, is an example of the work we do in hardware security, fault tolerance. And you've seen other works like Raider. The refresh is on memory and storage systems and efficient systems. I'm very excited about hardware-software cooperation, as you will see in this course. And that's essentially how things are being designed today. You need hardware-software cooperation. And you need to really understand both to be effective in building complete systems that are efficient at solving problems. And genome analysis and application algorithm hardware co-design is another of my interests. And I'd be happy to talk about any of these if you have interest. So related to this, I will say that this course might seem like it's only computer hardware, but it's not true. That's not the right way of looking at it, I think, because we will cover a lot of software. And at some levels, hardware and software are not really that much different from each other. Where do you draw the boundary? Well, it's not clear, because you're going to actually program hardware just like it's software, if you will, as you program the FPGA. Right? FPGA is a very flexible substrate. It's hardware in the end, but you're going to program it through software. And you will be much more capable if you actually master both hardware and the software and understand them. And the interface between them. So if you want to, in the future, design a very capable system, a very efficient system, you will have to do both, basically. You cannot just rely on an efficient computer that's designed by somebody else. Maybe you'll be able to get away with it, but you really need to understand what's going on in the hardware of that computer to be able to program it. And essentially, you can develop much better software if you understand what's going on underneath, as we've discussed. And you can also design better hardware if you understand the software. And that's actually very important. If you want to become a software designer, you'll need to understand hardware. If you want to become a hardware designer, you'll need to understand software, because software is what runs on the hardware you design. And if you make the wrong choices, the hardware may be extremely difficult to program, as we will see in some examples later on. And you can design a better computing system if you actually understand both. So my goal is to actually help you understand both in this course. So it's, the focus is really at the hardware-software interface and the microarchitecture. We'll start with logic today, which is at the bottom of the microarchitecture, actually lower than microarchitecture, but we're going to work our way up. And we will focus on trade-offs and how they affect software as well as the hardware designer. So we call the four mysteries. Four mysteries are very good examples of this, actually. Even though the four mysteries are fundamentally hardware problems, that's why I chose them, they really affect software very heavily. Like the simple bit flip in hardware, the rope hammer problem, affects pretty much all the software stack on top of it, right? The security. Meltdown and Spectre, it affects the software stack on top of it. Memory performance attacks, as I just gave you an example, if you don't provide the right primitives in hardware, you cannot do cloud computing with service level agreement guarantees, because you cannot guarantee that the performance of this particular program is going to be what you promise if you run it together with some other program. So what do? You don't run it together with some other program, so you waste some resources. So there's a trade-off between performance guarantees and efficiency in that case. Okay, so it's all about the trade-offs in the end. So you can trade off one thing that you want to do for another thing, but the hope is that we want to get all of them at the same time as much as possible. Okay, so what do I expect? I think the required background, very quickly, you're here, so hopefully you have all the required background, but I will say that you should know about binary numbers and binary arithmetic. Does anybody know that? Binary numbers, everybody knows binary numbers? Okay, good. If you don't know, there are lecture notes that are supplementary that's on the website. Download them, use them, it's very simple. And actually the books cover them. I believe chapter 2 in Pat and Patel covers binary numbers, so please know that. Reading material week 1, and hopefully you'll be enthusiastic to learn and think and common sense. I know this is a required course, so maybe one of the reasons why you take it is because it's required, but it's all about the mindset. If you come here with, oh, I got to take this course because it's required, maybe you don't learn as much. But if you come here and say, okay, it's required, maybe it's required for a reason. So let me try to make the best out of it. So if you're given lemons, make lemonade at least. Don't throw the lemons. So that's what I will suggest, basically. It's true for everything you do in the world, I think. If you have the right mindset, you'll get the most out of it. And common sense, hopefully. Yeah. Common sense meaning that don't cheat. Okay. Okay, so learn the material thoroughly. These are, this is more important, perhaps. Attend the lectures, do the readings, do the exercise, do the labs. Actually, I frankly don't care if you attend the lectures. It's good to have an audience here who's interactive. But if you learn better by going through the videos and understanding them, that's fine. I'm not going to take attendance or anything. So feel free to find the best way of your own learning. As I said, learning is very heterogeneous, and you will be much more effective in learning if you figure out what is the best way you yourself learn things. And once you figure that out, I think you can actually pretty much accomplish anything in the world. But of course, attending the lectures and asking questions may help if you have that sort of learning type. If you do the readings, do the exercise, do the labs. Of course, I think this course will require a lot of work, no question about that, but it'll be a fun and informative course. I would suggest asking questions, taking notes, participating. That's good. Feel free to ask questions. I don't mind getting interrupted. If I get interrupted too much, I will adjust the material somehow. Perform the assigned readings. They will help you, as I said. Come to class on time. That helps. I don't know why it's highlighted. If you don't want to come to class, you can remove the highlights. Okay, start early, do not procrastinate. That's important. So if you really want to not fall behind, I would suggest keeping a good schedule. If you want feedback, come to office hours. We have a nice team of teaching assistants, essentially my postdocs and PhD students. You know, Juan over there, Hassan, John, Luis, Nika. I see a bunch of people over there, and Mohammed is sitting over there, since he wants to get a different perspective. Yeah, it's good to change your location sometimes if you want to get a different perspective. That helps, you know. Now that makes my life hard because I cannot find you, but that's okay. No problem. Okay. So this, I really like this word. Does anybody know about Louis Pasteur? Like pasteurization? That's why you can drink milk without dying today. That's one example of that. Yeah, basically, he said chance favors a prepared mind, and this is really absolutely true, I think. If you've done your homework if you actually prepare, then you're more lucky, somehow. That's how the luck magic works. Of course, you cannot guarantee that you will get more lucky, but you're actually biasing the coin a little bit by actually doing what you're supposed to do. And this is him looking at you very seriously. So listen to him, if you don't listen to me. Okay, so how you prepare and manage your time is very important. There will be line assignments as we've discussed yesterday, and they will take time. You need to start early and work hard. It'll be a heavy course, I don't need to say that, but basically, hopefully, if you have the right attitude, you'll learn a lot. You'll understand how a microprocessor actually works from the ground up, and today we'll start with the really ground up. And hopefully this will change the way you think about things. If those trade-offs are really important. When I first took my Introduction to Computing Systems class, it was actually based on the Pat and Patel book. I took it from Yale Pat, who was one of the authors of that book, the blue book, the second edition. It wasn't a book at the time, it was lecture notes. It was put into the form of a book later on. And it really changed my life, basically. I really thought about things very differently. And I said, oh, I had zero idea how computers work. Now I have a lot of idea. But now I have maybe other ideas on how other things work in the world also. Okay, so I already said this. Hopefully you're going to do that assignment. But basically, we'll start with the fundamentals first. So clearly, we want to use computer actually as an enabler for the future. So your goal later on may be using what you learned from this course for enabler of your future, or enabler of a better future of whatever that you decide to do. But we need to start with fundamentals first. Basically, you can only change the world if you understand it well enough. And we will need to understand it well enough. And that requires understanding how these things work first. Especially the basics, fundamentals. That's why the focus of the first two lectures, right? First lecture actually was on these beautiful architectural structures, right? And there are fundamental principles behind those architectural structures. Now we are going to cover the fundamental principles of design and computer architecture. And these things are important because they last for much longer than a human lifetime, much longer than that, actually, much longer than hundreds of years, potentially. If you know the fundamentals of electricity, for example, they will last for a long time. Physics also lasts for a long time, right? So we'll see the past and present dominant paradigms and their advantages and shortcomings. So we'll see the trade-offs. And what remains fundamental across generations, hopefully. And what techniques you can use to develop and solve problems. So let's take a look at those fundamental concepts. And remember, we're going to, so basically a computer, the first question is, what is a computer, right? A computer is something that computes, but it doesn't look like that. It basically has three components: computation, communication, storage, and memory. And as I said earlier, today we know how to do this computing well, but we're actually bottlenecked by moving data. Basically the communication, memory, and storage unit. And if you really have time, this is a beautiful paper by John von Neumann, who essentially invented computer architecture to begin with, that talks about the von Neumann architecture in 1946. It's not easy to read, but it talks about the critical components of computer. And we'll put this up on the website. It's not required reading. If you, for example, are unable to sleep at night, you may want to read it and see how it goes. Okay, so basically, you have a processing unit, you have memory, and you have I/O. In this course, we're going to overwhelmingly focus on processing unit, computing unit. We're going to understand how it works. We're going to look at different paradigms of designing it. And we're going to focus a little bit on memory after that. We talked about memory, how important it is. Unfortunately, we don't have time to talk about memory a lot. But toward the end of the course, we're going to focus more. While we're focusing on computing, and we're going to talk about memory also a little bit, but we're never going to go into the really big lectures on memory. We're going to build it, of course, because you'll need memory to actually form the processing unit. You need a register file. We're not going to talk a lot about I/O, but this is always present. The wires that you're going to put in your FPGA are going to be I/O. That's interconnect, basically. And this is very much intertwined inside the processing unit, inside the memory unit, in components connecting it, but just we don't have time to focus a lot on the I/O component. But to have the big picture, you need to know that it exists and it's always there. Okay, so essentially we're going to start with this part and then we're going to jump up and down. So let me give you an overview of the topics before we take a break. So basically what we will cover in the entire lecture is we're going to start with combinational logic, talk about hardware description languages, sequential logic, timing, and verification, and these will be in the logic layer over here, mostly. And then we're going to switch to the hardware-software interface a little bit. Of course, we're going to talk about microarchitecture a little bit over here also. And then we're going to switch to the hardware-software interface, talk about the ISA. We're going to look at two different ISAs, MIPS and LC3B, because fundamentals are the same across different ISAs. It's just the design trade-offs are different. And MIPS assembly programming, we're going to do some assembly programming. And then we're going to go into the processing paradigms. We're going to talk about different microarchitectures, single cycle, multi-cycle microprogram. We're going to talk about pipelining. All processors that we have today are pipelined. This is a fundamental principle. It's like an assembly line, how you produce a car. You have a pipeline over there. Processors work the same way. We're going to talk about different issues and out-of-order execution. And then we're going to talk about other processing paradigms and memory and cache and virtual memory. So, okay. Basically, toward the latter part of the course, we're going to broaden up a little bit. So we're going to start with the logic, but we're going to broaden up, and we're going to talk about even programming GPUs at some point over here. Okay, but this is a great place to stop, although I'm 1 minute late compared to the planned location where we were supposed to start. So let's take a break. Let's be back when the bell rings. So let's continue where we left off. This was a very convenient place to take a break. Remember, the last slide was this. Basically, we're going to build up to all of these paradigms. But to be able to build up to all of those paradigms, we really need to start with, do you prefer it open or closed? Closed. I think so too. Probably it's more airy open, but it's also more noisy. That's a trade-off between air quality and noise. Okay, to be able to build up to all of these, we'll start with the very basics. So basically, this is what we're going to look at today and tomorrow into the next week, not tomorrow, next week. Building blocks of modern computers, transistors. We're going to start with that. We're going to build logic gates. We're going to cover Boolean algebra. Have you guys covered Boolean algebra before? You know about that? Boolean equations. Who doesn't know Boolean algebra? Some people don't. That's good. Who knows Boolean algebra? Okay, that's what I would expect. I assume you've taken a discrete math class? Yes, who has taken a discrete math class? Okay, who has not taken a discrete math class? Okay, then you should know about Boolean. Okay, except for a couple of people. People should cover Boolean algebra and discrete math. Okay, anyway, we're going to cover it to some degree. It'll be fun, because this is really the basis of logic design today. We're going to cover it in a rigorous fashion, and then we're going to see how you can actually minimize circuits using Boolean algebra. So we're going to look at combinational circuits, different types of elements. I'm not sure if we're going to get there today. If not, next week. And then we're going to use Boolean algebra to represent combinational circuits and minimize logic circuits. So if time permits, should actually be here and here also. Okay, so we're going to look at microprocessors. Basically, what we're going to do in this course is look at the fundamental principles of microprocessors, and you're going to implement them on an FPGA. So basically, you're going to use this to actually implement a microprocessor inside the hardware of an FPGA by reconfiguring the different logic blocks that Hassan talked about last time, like the lookup tables, for example, or the wires. You don't need to know about the FPGA architecture, but FPGA architecture is built based on logic gates that we're going to talk about today also. It's also based on transistors. Underneath, this and this is exactly the same. It's, well, exactly the same in the sense that it's built off transistors and logic gates, but these are configured in different ways. In an FPGA, transistors and logic gates are such that you can configure them, you can program them using the hardware description language that we're going to talk about. And on an FPGA, essentially, you can do anything. It's a Turing-complete machine. You can emulate how the microprocessor operates by programming the gates and the lookup tables and the interconnect on the FPGA. There's also custom ASICs. These are application-specific integrated circuits. We're not going to go into these, but these are basically chips that are designed to run a particular program only, or a particular class of programs only. For example, Google's tensor processing unit that was covered in the first lecture, which is designed for running machine learning applications across Google's data centers. It's based on a custom ASIC. It's called tensor processing unit, TPU. There are other sorts of ASICs that you can have, video processing engines, for example, that are just there for video processing and putting the data out somewhere else. Those are custom ASICs. Essentially, you can use these to do one task extremely efficiently, But you cannot program these like you would program FPGAs or microprocessors in general, because they're designed just for the task at hand. Tensor processing unit just does particular machine learning algorithms that is designed to accelerate. It's designed to execute. Okay, so they all look the same underneath. All of them actually, this is based on transistors and logic gates, except they're hardwired to do a particular task really well. So in short, very quickly, this is the common building block of computers, microprocessors. We will learn about them. We will use FPGAs that are reconfigurable, that are much more flexible, that can implement any circuit in a flexible way to actually emulate a microprocessor. And in ASIC, you customize essentially everything for the algorithm that you're executing. So the programming time here is relatively quick. You run at a high level, program in a high level language. Assembly language is higher level than binary, as we will see. But it doesn't take long. Here it takes a bit longer. Here, basically, you need to really design the hardware to execute a particular algorithm, so it takes a long time to do this. But the performance you get on, this is very good at general purpose performance. FPGA may be slightly higher depending on how you configure the circuits. And this is the highest performance you get for the particular algorithm that you're interested in. Of course, if the algorithm doesn't match the ASIC that you built, if you're trying to run a database on Google's tensor processing unit, it just doesn't work, right? Because it's not designed for the database, right? So you have to go back here or here. Okay, so basically this is ubiquitous, it's simple to use. FPGAs are good at prototyping, but this is actually changing. This is an old slide. People are using FPGAs for accelerating many applications. As I said earlier, Microsoft, for example, has FPGA-based systems where in their data centers, they use the FPGAs for machine learning training. They call it the brainwave system, aptly. It's a nice acronym, so you can take a look at it if you're interested in that. But FPGAs are being used for real computation, not just prototyping right now, but we're going to use them for prototyping in this course. We're going to use FPGA to prototype a microprocessor. And we're not going to touch this because we're not going to build an ASIC in this course. If you're really interested in doing that, you can take advanced course on VLSI design, for example. Okay, I'm not going to go through this in detail, but let me actually say, basically, languages that you use here are high level. Here we're going to use Verilog, lower level. And this is also programmed with Verilog. People have tried to configure FPGAs with high-level languages for a long time. That's not that easy because doing the compilation from like Java into RTL, register transfer level, it turns out it's not very easy to make it efficient. But programming language is a programming language. Basically, you program it. It enables you to do some things, and you'll learn it. It's not that different from regular programming languages. The difference will be you're going to be programming the hardware, bits and gates, making the hardware do the things that you want it to do. The difference will be actually, I think that's a crucial difference. It's going to be parallel programming from the very beginning, in the sense that hardware is inherently very parallel. There's something going on in this part of the circuit. At the same time, there's something going on in this part of the circuit, and you need to make sure that you need to orchestrate. Those things are going on concurrently at the same time without conflicting with each other. And we will see this more, and as you will design the program on your FPGA, you will see this more. And if you really have the right mindset, you will get the best out of this course by understanding the parallel programming nature of hardware. Now, unfortunately, these are not the best languages for parallel programming, but these are the languages that are used everywhere in the world pretty much, Verilog, AMI, HDL. Okay, and there are some main companies over there. I'm going to reduce the, okay, because I can hear myself. Okay. As I said, so we basically want to learn how these work, and we're going to look a lot into those things by programming these things and using this language. Okay, so now let's start with the building block of modern computers, and if we have to name a single building block, that's not going to be an electron, that's going to be a transistor. I'm going to ignore the electrons. So we have to start with some abstraction level, and that abstraction level is a transistor. So essentially, computers are built from very large numbers of simple structures called transistors. And if you look at this number over here, it's very small. In 2000, Pentium 4, the flagship processor of Intel at its time, had 42 million transistors. In 2016, another flagship processor had 3.2 billion transistors. MOS, I'll define a little bit, metal oxide semiconductor, that's what the transistor is composed of. And this lecture basically talks about how the MOS transistor works. We're going to cover this right now. as a logic element. Oh, before I go, this is 2016. In 2019, we're over 10 billion transistors, I think. I don't know, actually. I cannot keep up with this. Maybe it's 20 billion. I'm pretty sure it's going to be 20 billion soon if it's not right now. Basically, we're going to cover how the transistor works as a logic element. So basically, we're going to start with a device. You can think of transistor as a device which moves electrons, or which enables the movement of electrons. Hopefully you've had physics at some point in your life, so you learned about electrons. We're going to use transistor as the abstraction level to build logic. Basically, how do we connect these transistors to form different logic gates? And then we're going to move to how these logic gates are interconnected to form larger units that are needed to construct a computer. Basically, we're going to move to microarchitecture and ISA. Okay, so let's start with the transistor. Has anybody learned about transistors before? Yes? Who says no? Okay, that's good. Where did you learn about transistors? High school? Okay, I see some people saying yes. Not everybody learned it, I guess. So basically, you form a transistor by combining conductors, metal, insulators, oxide, and semiconductors. Actually, this metal is outdated already, because people usually don't use metal because they're very high temperature processes that are employed, so people have moved to polysilicon right now, but that's okay. It's still called a metal oxide semiconductor. We're not going to break that abstraction layer for a while. So essentially we get a transistor, which we'll call the MOS transistor, and it looks like this. You don't need to know exactly how it operates for the purposes of this course. If you want to know, go to your readings. Your readings slightly break the abstraction, and we'll talk about how a transistor operates, but they don't go into a lot of detail. If you really want to know, you should take a microelectronic design and circuits course. That's where you will really learn. Basically, a transistor consists of a gate and a source and drain. This is the cross section. If you actually cut the silicon in half and happen to cut through a transistor, you will see it this way. There are semiconductors over here, there's an insulator over here, and there's a conductor over here, polysilicon. And basically, you apply voltage to the gate, and depending on the type of the transistor, the application of the voltage turns on or off the transistor. What does that mean? Turning on the transistor means that the source and drain get connected and current flows. Electrons or holes flow from the source to the drain of the transistor. That's essentially what it means. So why is this useful? Because you can combine many of these to realize simple logic gates. And as I said, the electrical properties of metal oxide semiconductors are well beyond the scope of this course. And we're going to treat this transistor as a wall switch, as I will see in a little bit. Basically, the electrical properties are below our lowest level of abstraction. If you want to change the transistor, or if you want to do some things with the transistor, something that are different from the abstraction level that I'm going to tell you, you will really need to understand those electrical properties. But we're not going to go to that level, and you're not going to be expected to know how a transistor works for this course. So there are two different types of MOS transistors that you should know, though. One is N-type, and the other is P-type, negative, positive. And N-type looks like this. Basically, if you apply high voltage to the gate, the source and drain get connected, and the transistor turns on. So it becomes a conductor at that point. It becomes a switch. It gets switched on. P-type is exactly the opposite. Basically, you need to apply low voltage or 0 volts to the gate so that you turn this on. That's how it becomes a piece of wire, essentially. So they both operate logically very similar to the way wall switches work, as I kind of described right now. Has anybody used wall switches? If you want to turn on the light, yes, good. If you haven't used it, you can try it out. Maybe don't do it right now. But basically, whenever you press the wall switch, something gets connected and lights turn on. And whenever you press it again, that thing gets disconnected and lights turn off, right? That's essentially this. You apply high voltage to the N-type transistor's gates, and it becomes like a wire. It gets connected. You apply low voltage to N-type transistor's gates, and it gets disconnected. Basically, it becomes an open circuit. It doesn't conduct. As a result, it's like a wall switch that's not turned on. P-type is exactly the opposite. That's why, so this little dot over here says that it's the negated value. This dot says, there's no dot over here, so you apply high voltage, this gets turned on. For this to get turned on, you have to apply the negative of high voltage, which is low voltage, or the complement of high voltage, which is the low voltage, to turn this on. Okay, how does the transistor work? Again, abstraction level is like a wall switch, right? This is our bulb, and we have wall switch, and if you go and press the button over there, your power supply gets connected to the bulb, and for the lamp to glow, you actually need to connect the power supply to the bulb. Okay, so very similar to this analogy over here, in order for the electrons to flow through a piece of circuit, there must be a closed circuit from the power supply to the lamp and back to the power supply. And by turning on this wall switch, we're actually enabling that closed circuit such that the power supply can circulate power into the lamp over here, there. But basically, the lamp can be turned on and off by simply manipulating this wall switch to make or break the closed circuit, to keep it closed or open. Hopefully that's a simple abstraction, right? You turn it on and you turn it off. And you could keep doing this forever. Probably not a very useful exercise to do it forever. So basically, instead of that wall switch that's over there, we're going to use a transistor. We could use an N-type or P-type transistor to make or break the closed circuit. Basically, keep it closed or keep it open. So this is our transistor abstraction. You have the gate, and you have the drain and source. You don't need to exactly know what the drain and source are. Those are different parts of the transistor. Maybe you know based on the course that you had, but I'm not going to hold you responsible for it. Basically, this is a schematic of an N-type MOS transistor. If the gate of an N-type transistor is supplied with high voltage, as I said earlier, just to reiterate, the connection from the source and to drain acts like a piece of wire. So you get a closed circuit in that case. So electrons flow from the source to the drain. Well, okay. And depending on the technology, that voltage could be different. We're not going to go into exactly what that voltage is. That those voltages are reducing, which is what is making transistors much more efficient. We were able to reduce those voltages a lot. That's why things are efficient. But if you go, this is also dependent on where these transistors are. For example, if you're looking at your SSD, solid-state drive, those voltages are very high today, so that you can actually power up those big lines, like 5 volts, around that. Sometimes it could go even to up to 10 volts. But today, if you look at the microprocessor over here, it's much lower than 1 volt, the voltage that you need to apply to make it work. And that's essentially why these are more energy efficient, because that voltage is dropping. Okay. If the gate of the N-type transistor is supplied with 0 volts over here, the connection between the source and the drain is broken. As a result, you get an open circuit, so this doesn't conduct anymore. So drain and source are not connected to each other. Okay. Clear? So let's take a look at some examples. We're going to iterate some of this a little bit more. So this is the N-type transistor in a circuit with a battery and a bulb. Basically, this person applies 0 volt over here. The N-type transistor turns off, so the bulb doesn't glow because the circuit is closed. Now, if you go and electrify and apply 3 volts, magic, the circuit starts conducting, so the power moves from here to here, and as a result, you have an electron flow. So this thing glows. So it's basically a wall switch, right? That's our abstraction. And you can think of this as a shorthand rotation over here. So basically, this is just to set the terminology, because you're going to see these figures in a little bit. This is the power supply, high voltage. This is the ground, low voltage. And this is kind of our abstraction. By applying voltage to this gate, what happens is you're causing high voltage to this gate, you turn it on, and you're causing the electrons to flow from high voltage to low voltage, and in the process, turn on the light bulb. If this circuit is open, the electrons don't flow from the high voltage to the low voltage. Okay, and so what is P-type? P-type works exactly the opposite fashion from the N-type transistor. When you apply, so this is the N-type, you need to apply high voltage to connect the source and drain. High voltage in our case, let's say 3 volts. That's not realistic in existing systems, but I'm going to use 3 volts over here. So for the P-type, you do exactly the opposite to turn on the transistor. The transistor gets turned on if you apply low voltage, meaning 0 volts to the gate. That way, drain and source get connected. So I say transistor gets turned on. That means transistor acts like a piece of wire. Source and drain are connected to each other, so electrons are flowing. If the transistor is turned off, then drain and source are not connected to each other, so it's an open circuit. Electrons are not flowing. So I'll use this terminology. Hopefully it's obvious. Okay, any questions? That's our abstraction. Now, if you go underneath one level, how do these transistors exactly work? There are a lot of design trade-offs and design choices, which we're not going to cover because there are many, many different types of these transistors also. That's a whole course in itself, the lower level. But we're going to now start building to the upper levels, now that we have the abstraction. So we're going to go one level higher in the abstraction. Now that we know how a MOS transistor, metal oxide semiconductor transistor, works, how do we build logic out of these MOS transistors? Basically, we're going to construct basic logic structures out of individual transistors. And these logical units are named logic gates. And we're going to see a bunch of examples of the logic gates. And these logic gates implement simple Boolean functions, logic functions, that operate on binary values. So let's take a look at that. So modern computers use both N-type and P-type transistors. There are actually trade-offs in N-type and P-type. For example, P-type is, as we will see in a little bit, I don't want to break the abstraction, but let's continue. We'll see the difference a little bit. So you use NMOS and PMOS. This is called complementary metal oxide semiconductor technology, and you need to use both to make things work. And the simplest logic structure that exists in a modern computer is what I'm going to show you next. It looks like this. And maybe you can tell me what this is. Remember, this is a P-type transistor. It gets turned on when the input is low, 0 volts. This is an N-type transistor. It gets turned on when the input is high, 3 volts. So what does this do? Okay, it's an inverter, yes. So everybody see it? If you don't see it, I'm going to go through it, basically. What it does is basically it inverts the input. If the input is 0 volts, you'll get 3 volts out here. If the input is 3 volts, you get 0 volts out here. And you can encode 0 volts as 0, 3 volts as 1. Now you built a Boolean inverter that takes a 0 to 1 and a 1 to 0. And this is the simplest, well, one of the simplest logic gates that you have. Okay, I guess I already asked the question. So let's take a look at this. What happens when the input is connected to 0 volts? So let's assume this person is connecting the input to 0 volts. And we have the P-type transistor. That gets turned on, right? And the N-type transistor, that gets turned off. The volt switch is broken over here. What does this mean? 0 volt, the ground is not connected to the output. But 3 volt, the power supply is connected to the output. So the output becomes 3 volts. So if you input 0 volts, you get 3 volts out. Makes sense, right? You've inverted what you had in the input. Okay, basically P-type transistor pulls the output up, and N-type transistor cannot pull the output down because it's not, the transistor is not connected. It's open circuit at that point. If it were actually somehow pulling the output down, then you have a problem, right? But that's why it's complementary. When this is turned on, this is turned off. When this is turned on, this is turned off, as we will see. What happens when the input is connected to 3 volts? We're going to do the same exercise, except we're going to connect 3 volts to the input. If the input is 3 volts, this gets turned off because P-type transistors get turned on when they have 0 volt input in the gate. And this gets turned on because the N-type transistor gets turned on when they have high voltage, or 3 volts in the gate. So it looks like this now. This transistor is turned on, this transistor is turned off. And the ground gets connected to the output, and the power supply is disconnected from the output. As a result, you get 0 volts on that line. Essentially, N-type transistor pulls the output down. Electrons flow. Make sense? So this is the basics of complementary metal oxide semiconductors. It's complementary because they have a P-type circuit and an N-type circuit. And when the P-type transistor is turned on, this is turned off in the previous example. And with it, this is turned off, this is turned on. It's complementary operation. You don't want both of them to be turned on at the same time, because that leads to a short circuit. You don't want both of them to be turned off at the same time, because that leads to undefined value in the output. You need exactly one part, either the power supply or the ground, to be connected to the output for the circuits to work. And that's essentially how computers are designed. Okay, so this is called the CMOS NOT gate. It's essentially NOT, or NOT of the input, which is an inverter or complement of the input, right? So why do we call it not? I think it's obvious, it's an inverter. So this is really a digital circuit. Now you can assign logical values to the voltages, right? You can interpret 0 volt as a binary 0 value. You can interpret 3 volts as a binary 1 value. Now you can do binary inversion, not. You don't have to do this. You can interpret 0 volts as a binary 1, and you can interpret 3 volts as binary 0. As long as you're consistent in your interpretation, no problem. We're basically renaming 0 volts to 0, binary 0, and 3 volts to binary 1. Now we can do binary logic. Okay, now we can actually form a truth table of how this transistor works. So with any logic gate, you can describe any logic gate or any circuit with a truth table. What is a truth table? A truth table basically, for every possible value of the inputs, it gives you all the values of the output. So this is the input. We have A, the output is Y. We enumerate all possible values of the input. In this case, input is a single bit. It could be 0 or 1. And the output, then the truth table tells you what is the output if the input is 0, what is the output if the input is 1. Okay? And in this case, we actually have intermediate parts of the circuit that are also shown. So if the input is 0, the output is 1. Why is the output 1? Because a P-type transistor turns on, and N-type transistor stays turned off. That's how the output becomes 1, because the 1 value at the power supply gets connected to the output. If the input is 1, the output is 0. Why is it 0? Because if you actually put 1 over here, the N-type transistor turns on, P-type transistor turns off. As a result, the 0 value at the ground gets connected to the output. So hopefully it's clear. And this is the truth table that you have. Unfortunately, that thing I haven't fixed yet. Basically, it's A bar, the complement of Y. Y is equal to A bar, and this is our truth table over here. So, and this is also denoted like this. Basically, this is the symbol for the inverter. It's a triangle with a circle after it. Circle means immersion. Every time you see the circle, that's immersion. If you get rid of this, actually, it turns out it's a buffer, which we will see later on. Okay, so we call it a NOT gate or an inverter, and truth table, as I showed you earlier, tells you what would be the logical output of the circuit for each possible input. So in this case, you have only one input. So the truth table has 2 entries, or 2 rows over here, and you get the possible outputs. Okay, we're going to form truth tables, and you can express any circuit with a truth table, basically, like any Boolean function. Okay, so let's build more complex gates. Yes, please.
Why can't you not just use one P-type? Because, I mean, it does exactly what you want it to.
How do you pull it down?
If you just, I mean, the P-type just lets the, if I put this correctly, the P-type, if you put a high, then it lets no flow through. So it's basically exactly what you want. You just take it.
No, if you put a high over there, what happens is, okay, assume that this doesn't exist. That's what you're suggesting. If you put this to a high, this gets closed. Meaning that the output is not connected to anywhere. Right? Okay, maybe you get rid of this and the output is connected to 0, right? That's what you're saying.
Yeah.
Okay, that works. Okay, now let's apply 0 volts over here. What happens? Then it flows over here, right? But you have a short circuit now, right? This doesn't become 3 volts. The current flows that way. So you need to disconnect. That's why you need to pull up and to pull down at the same time. Okay. Okay, so let's build more complex gates. What is this one? You need to think about this a little bit. It has 2 inputs, A and B, and it has 1 output. And you can see that the P-type transistors are connected in parallel to the output, and the N-type transistors are connected in series to the output. And input A goes to P1 and N1, and input B goes to P2 and N2. Okay, let me give it to someone else. Yes? It's a NAND gate, I hear. Does everybody agree? Does everybody know what a NAND is? Okay, now you will see what a NAND is. So it's a NAND gate. It's called a not AND gate. Basically, so let's take a look at how this behaves. If both inputs are zeros, let's start with that. What happens? Both P1 and P2 get turned on, and these get turned off, so you get 3 volts, right? So you get a 1 at the end. If any of the inputs are zeros, let me generalize it. One of these gets connected, either P1 or P2 turn on, and 3 volts get connected to the output. And if either of these is a 0, 0 volt doesn't get connected to the output, right? Because one of them will definitely turn off if either of these is a 0. That's the beauty of the series connection. So if A or B is a 0, what happens is 3 volts get connected to an output, and 0 volts doesn't connect it to the output. So if either of these is a 0, then you get a 1 at the end. Okay, now let's take a look at what happens if both of them are 1s. If both of them are 1s, you get high voltage, both of these turn on. You get low voltage over here, these turn off, right? Because you apply high voltage and P-type transistors turn off. So the only case you get a 0 volt, a logical 0 at the output is when both A and B are 1s. All of the other cases, when either A or B is a 0, you get a 1 at the output. So this is a NAND gate. Why is it called a NAND gate? We will see. So basically, P1 and P2 are in parallel. Only one must be on to pull the output up to 3 volts. So in all cases where P1 and P2, either of them is turned on, meaning that either A or B is 0, you get a 1 at the end. And the only case you get a 0 is when both A and B are 1. So if you look at this function, this is exactly the complement of an AND, right? And if you want to take the AND of A and B, logically, the truth table you should get should be 0, 0, 0, 1. But you get exactly opposite over here. You get 1, 1, 1, 0, which is the complement of the AND, which is called a not AND, or in short, NAND. That's the NAND gate. Make sense? You just need to go through what happens for each input case, basically. If the input is 0, 0, P1 and P2 get turned on, N1 and N2 get turned off, you get a high voltage at the end because 3 volts get connected over here. That's true whenever A or B is 0. Only case where that's not true is when A or B are both 1. In that case, you get N1 and N2 in series turned on, they get connected to the output, and these are disconnected because these transistors are turned off. As a result, you get 0 volts. Okay, so this is the next basic circuit that we have. It's a NAND. Okay, keep this in mind. And it's denoted like this. It's the complement of A and B, or AB not, basically, A and B not AND. And it's denoted this way. It's the AND, but not. It turns out CMOS is very good at inverting. It's called inverting logic. You can build gates that invert really easily because of this complementary nature. Because P-type is over here, N-type is over here. You need to think about this a little bit. So you're very good at building these inverting logic. And if you want to get an AND, it's not that easy just by doing this. Okay, before I move on, this is the truth table that we have for NAND as I just showed you. This is the concise truth table as a logic gate. If either A and B is 0, output is 1. If both A and B are 1, the output is 0. Okay, so how do we build AND? So as I said, CMOS is very good at inverting. The simplest thing that we started with an inverter, right? We inverted the input. NAND didn't give you an AND, it gave you an AND. It gave you an inverted AND. So we build these inverted circuits. So in order to get the AND gate, you can think about this a little bit, how do you construct the AND gates, but you'll need to learn a little bit more about transistors if you want to understand really well. It turns out it's not easy to build an AND gate just like this. AND gate comes with, well, AND gate is like this, right? Basically, if it's the AND of A and B, the logical structure should look like this, the truth table. If both A and B are 1, you should get a 1, which is exactly the opposite of NAND. You basically have 2 logic gates. You first have the NAND, and then you invert the output. That's how you get an AND. It's logical, right? Logically, the NOT AND, and then if you put a NOT inverter after a NOT AND, you get the AND. The reason we do it this way is because CMOS is not good at building non-inverting logic. It's very good at building inverting logic because of the way PMOS and NMOS transistors are structured, pulled up and pulled down. Okay, basically we make an AND gate using 1 NAND gate and 1 NOT gate. You could think it's wasteful. Well, maybe it's wasteful. But it's actually not that wasteful because it turns out NAND gates are extremely good. NAND gate is a universal gate in the sense that it's a functionally complete logic function. Meaning just using NAND gates, you can build anything. You don't need anything else, just NAND gates. Think about this a little bit. You can prove this to yourself, actually, that's going to be one of the points over there. Just using NAND gates. That's true for NOR also. Just using NOR gates, you can build any logic function. That's not true for AND, it turns out, because inverting is really important. You have to invert things to be able to do things. Okay. Okay, so basically we built some circuits, these logic gates. This is the logic gate, this is the truth table, and this is the transistor level implementation for the NOT gate inverter. This is the logic gate for NAND, this is the truth table, and this is the transistor level implementation in CMOS. And for AND, this is the truth table, this is the logic gate, this is the truth table, and this is the transistor level implementation. Yes? Could you say it again? Yeah.
Is it just because our logic is very easy to build, or is it that we don't know any gate that's...
Yeah, as far as I know, we don't know any gate that works really well. Because CMOS is really inverting logic. You can try it. You need to learn a little bit more about transistor implementation, but this is the simplest I know that works well. If you're interested, look at chapter 1.7, I think, or one of the chapters in Harris and Harris. It will give you more detail, but it won't give you different alternatives. You really need to take a microelectronic design course if you're interested. Okay, this is our level of abstraction. So basically, similarly, you can do OR, right? I didn't give you OR here, but an OR, it turns out NOR is easier to build than OR. So you start with a NOR. This is not a NOR, this is an AND. What is a NOR? NOR is essentially a NOT OR. Basically, you take the OR of A and B and then NOT it. And the gate that implements NOR is exactly, it looks different from this because P1 and P2 will be in series and N1 and N2 will be in parallel. So that's the logic gate for NOR. And if you want to do an OR after that, you take the NOR gate, not this one, the one where P1 and P2 are in series and N1 and N2 are in parallel, and then you add an inverter at the end. That's how you get the OR gate. Now you can do OR as well. Okay, so this is a general form used to construct any inverting logic gate, such as NAND, NOT, NAND, NOR. I give you NOR when I discussed. Basically, you have the power supply, you have the ground, and you have the output. Power supply and out, between power supply and output, and you have the inputs, of course. You have the PMOS pull-up network, and between the output and the ground, you have the NMOS pull-down network. And you need to have both of them for the logic gate to work. The NMOS, and these are complementary to each other. When this is turned on, this is turned off. When this is turned on, this is turned off. And the networks may consist of transistors in series or in parallel. And as I said, when transistors are in parallel, the network is on if one of the transistors is on. When the transistors are in series, the network is on only if all transistors are on. And you need both of these to make it work. PMOS transistors are used so that you can get a 3 volt or logical 1 at the output. They're used for pulling up the output to a high value, logical 1. NMOS transistors are used for pull down. You need to pull down the value to a logical 0. And as we discussed, one of your colleagues asked, why not just have PMOS transistors? Because you would have a short circuit otherwise. So let's go into a little bit more over here. So exactly one network should be on and the other network should be off at any given time. Otherwise, you would get a short circuit over here. If both networks are on at the same time, there's a short circuit. This 3 volt gets connected to the 0 volts and basically likely incorrect operation. If both networks are off at the same time, nothing gets connected to the output, neither the power supply nor the ground. As a result, you don't know what the output value is. It's undefined, right? It's also called a floating value, or Z, in logic, as we will see later on. And this is usually not good, but a designer can use it for different purposes. Sometimes you don't care about the value, so you could actually enable this. Okay, let's dig a little bit deeper before we move on to the next lecture. Basically, I'm going down a little bit, breaking the abstraction layer a little bit. It turns out these MOS transistors are not perfect switches. I gave you the abstraction that they're perfect switches, but they're not perfect switches. It turns out that there's a reason why PMOS is at the top and NMOS is at the bottom, because PMOS transistors are very good at pulling up, passing ones well. But they pass zeros poorly. So if you want to put the PMOS transistors down and connect them to the ground, you have a problem. It doesn't work well. So it's not exactly a wall switch from that perspective. That's why you need to, if you want to change the structure, you need to know a little bit more. NMOS transistors, on the other hand, pass zeros well, but ones poorly. That's why they're good at pulling down, but they're not good at pulling up. So you don't want to put an NMOS transistor toward the top of the circuit. That's why we designed the way we designed them. I guess I already said these. That's why you have the pull-up network over here, based on PMOS transistors, and pull-down network over here, configured with NMOS transistors. And yeah, see, this is one section where you can go into a little bit more detail in transistors in Harris and Harris. So another question, which one is faster? Actually, there's another thing over here. This covers something else, but it turns out PMOS transistors are also slower, so NMOS transistors are faster because of the way things are manufactured. So how do you actually make things work that way? You can read some things. So which one's faster? Transistors in series or transistors in parallel? So if transistors are connected in series, and if you want current to flow from the high voltage to some destination, it's slower, right? Because you need to go through more transistors to go through that. Because each transistor has a resistance, and you have to actually go over that resistance. So series connections are usually slower than parallel connections. There's more resistance on the wire. And to alleviate this latency, you may want to get rid of these series connections as much as possible. And how do you design gates by getting rid of these series connections is out of the scope of this course. But you can see one example over here, which is pseudo NMOS logic, which you don't really need to know. But if you're interested, you can take a look at that section. Okay, a little bit more power consumption. And this is going to be the last slide I think we'll cover over here. Basically, these things consume power. We're not going to focus a lot on power, but keep this in your mind. They consume dynamic power, they consume static power. Static power is the power you consume when you don't apply any input to the circuit. The current somehow keeps flowing because these are not perfect switches, right? Dynamic power is the power that you consume when you apply some input. And this is expressed this way. It's proportional to the capacitance of the circuit, the square of the voltage, and the frequency at which you switch. I guess I already said this already. If you really want to understand why this is the case, you can take a look at basically you're switching the capacitor, charging and discharging the capacitor, and charging and discharging the capacitor takes CV square, and the frequency of switching multiplies how many times you actually consume energy by charging and discharging the capacitor. So you can express the circuit as a capacitor. And clearly, if your voltage is higher, you get a very high power consumption. If you're switching very frequently, you get very high power consumption. In existing systems, if you want to reduce the power consumption, we want to reduce the voltage as much as possible. Or we want to reduce the switching. But switching improves your performance, meaning that if you want to reduce your frequency of switching, you will impact your performance. So there's a trade-off between power and performance as a result of this. And if you really want to increase the switching, it turns out you need to increase the voltage, because that enables faster switching. So there is another trade-off between performance and power over here. Let me finish this quickly. This is the static power consumption. If the circuit is not turned on, it's leaking some current, and the power consumed is essentially based on how much that current is times what is the voltage of your circuit. And if you really want to learn more about this, you should take a look at Terrace and Harris chapter 1.8. Okay, we're going to start from here next week. Have a good weekend. I'll see you next week.